Hello and welcome to my lecture series for Control System 1. Myself, Suman Ghosh, as a course coordinator, assistant professor from Department of Electrical Engineering, Guru Nanak Institute of Technology, Kolkata. This lecture series for Control System 1 is designed for 5th semester BTech Electrical Engineering students. And this particular PPT is designed for lecture 9 and lecture 10. This is our 10th lecture. So these are the contents of lecture 9 and lecture 10. In lecture 9, we already discussed about signal flow graph, Mason's gain formula and one related example. And in this lecture 10, we will discuss some problems using Mason's gain formula, and next we will discuss on construction of signal flow graph from block diagram, and one more example we will see. So before going to our today's topic, let's take a quick recap of Mason's gain formula only. So this is our Mason's gain formula, where T is the overall transfer function of the system, delta is the determinant of the SFG. There is a rule by which we can calculate the value of the determinant of the signal flow graph. Pk is the gain of the kth forward path. Delta k is the path of delta, the part of delta not touching the kth forward path, and k is the number of forward path. So this is one example which I already discussed in our previous lecture. So in this lecture we will see problem number 2, where a SFG is given and you have to calculate the transfer function C by R. Now the first step of calculating the transfer function, we have to find the number of forward paths. How many forward paths is there? Here R is the input and C is the output. So how many paths? By using how many paths we will go from R to C. Just look at the figure. In this path we will go from R to C. So this is one forward path, and this is another forward path, and this is another forward path. So there is 3 forward paths. If we consider these paths, then these two nodes are more than once. So this is not a forward path. So here number of forward path is 3. So the Mason's gain formula, so by using Mason's gain formula, transfer function T will be 1 by delta P1 delta 1 plus P2 delta 2 plus P3 delta 3. Now what will be the value of P1? P1 means transmittance of the path 1. So if we consider this as a path 1, then the transmittance value of path 1 is multiplied. Just multiply the transmittance of the path 1, that is 1, G1, G2, G3 and 1. So ultimately we will get G1, G2, G3. So that is our P1. If this is our path 2, then the transmittance of the path 2 is 1, G4, G3 and 1. So G3 into G4 will be our P2, transmittance of path 2. And if this is our path 3, then 1 into G5 into 1. That is our P3. So G5 is equal to P3. Now we have to find the number of individual loops. So here, how many loops is present? So this is one loop, this is one loop, and this is one loop. So here two loops are present. So if this is L1, that is transmittance of L1, so that will be G1 into H1, and if this is loop 2, then L2 will be G6. Now just calculate or just find, is there any non-touching loops present? Here two loops are present. This is one loop and this is one loop. Is there any non-touching loops? Is these two loops has any common node? No, there is no common nodes for these two loops. So these two loops are non-touching. So L1, so we have to calculate the multiplication of two non-touching loops, all possible combination of multiplication of two non. So that will be L1 into L2, and we will get G1 G6 H1, multiplication of G1 G6 H1. So delta will be 1 minus sum of all individual loop gain products, that is L1 plus L2, plus sum of the all individual loop gain products of all possible combination of two non-touching loops. So that will be L1 into L2. So if you put all the values, then we will get this equation. Now what will be the value of delta k? Here k is equal to 3, so delta 1, delta 2 and delta 3 will be there. So before calculation of delta 1, we have to find, is there any loop present which is not connected with path 1. This is our path 1, this is our path 1, and these two loops are all connected with path 1. So there is no loops present which is not connected with path 1. So our delta 1 will be 1. Now if we calculate delta 2, so we have to find, is there any loop present which is not connected with path 2. This is our path 2, and these two loops are connected with path 2. So delta 2 will be again 1. And in this process, if we want to calculate delta 3, then we have to calculate the path. We have to find the number of non-touching loops which is not connected with path 3. This is our path 3, and these two loops are again connected with path 3. So delta 3 will be 1. So if we put all these values in this equation, then we will get that transfer function, which is our desired transfer function. Here is another one more example. Just go through it, simple and very easy way it is discussed. Here is another one example. Now, construction of signal flow graph from block diagram. All variables, that means input variable, output variable, summing points, takeoff points, all we have to represent by a nodes. And if a summing point is placed before a takeoff point, then point in the direction of signal flow, then the summing point and takeoff point are represented by a single node. And if a summing point is placed after a takeoff point in the direction of signal flow graph, then the summing point and takeoff point are represented by separate node. So these are the three basic rules which we have to keep in mind when we construct our signal flow graph from block diagram. Now this is our one example. Here this is the block diagram. We have to calculate the overall transfer function by using signal flow graph. So here all input and output summing point, takeoff point, all are considered as a node. So there is a R, it is a node, summing point, it is a node, takeoff point, it is a node, summing point, again it is a node, takeoff point, again it is a node, and summing point and takeoff point. Now in our rule, if there is a summing point before a takeoff point, then these two summing point and takeoff point are considered as a one node. And if a takeoff point is there before a summing point, then it will considered as a different node. So in this way we just draw the signal flow graph. We just draw the signal flow graph like this way. So this line is this line. Here one feedback is present. So here one feedback is present and this feedback is present. Here this is the feedback and this is the parallel path. This is our parallel path. So this line is this line is this line, and this line is this line. Now we got the signal flow graph from which we can calculate the overall transfer function using Mason's-Kane formula. Now before calculation, before applying Mason's-Kane formula, we have to calculate the number of forward path. Now what will be the number of forward path? Here two number of forward path is there. This is path 1 and this is path 2. This is path 1 and this is path 2. So P1 will be multiplication of the transmittance of the path 1, that is G1 into G2, and P2 will be transmittance of the path 2 multiplication, so that is G1 into G3. So here number of loops, how many loops are there, we have to calculate. So here 3 loops are present. This is one loop, this is another loop, and one more loop is present. Just look carefully. Starting from this, you just go from this. This is another loop. Starting from there, just go there. Starting from this, just go like this. So this is our loop, one loop, another loop. So if this is loop 1, then L1 will be minus G1 into G2 into H1. And if this is our L2, then L2 will be minus G2 into H2. And if this is our loop 3, then L3 will be G1, G2, G3, H1, H2. And we have to calculate, is there any non-touching loop present? Is there any non-touching loop present? There is 3 individual loop present, but all the 3 individual loops are connected with each other. So these are all touching loop. There is no non-touching loop. So our delta will become 1 minus L1 plus L2 plus L3. So after putting the value of L1, L2, L3, we get delta like this. And we have to calculate now delta 1 and delta 2. Delta 1 means first we have to find, is there any loop present which is not connected with path 1? This is our path 1 and all the loops connected with this path. So our delta 1 will be 1. And this is our path 2. Now we have to find, is there any loop present which is not connected with path 2? No, all the loops are connected with path 2. So delta 2 will again 1. So if we put all the values in this equation, then we will get the overall transfer function, that will be this. Okay, so there is another one example here. So this is our block diagram, and from this block diagram all input signal, output signal, summing point, takeoff point are represented as nodes, and just connect all the nodes like this. Then write down the Mason's gain formula in general, then again calculate P1, P2, P3, P4, that is the transmittance of the path 1, path 2, path 3 and path 4. Now here how many paths are present? Here 4 paths are present from which we can go from R to C. So this is our one path, this is our one path, and again another path is this, from starting to this end, this is our another path, and this is our another path. So here 4 paths is there. So we calculate the transmittance of this 4 path. Again, is there any how many loops are present? There is one loop present. This is one loop. This is one loop. So only one individual loop is present here. So L1 will be like this. There is no question for non-touching loop, as there is only present one loop. So delta is equal to 1 minus L1. So delta 1, delta 2, delta 3, delta 4 all will be 1. So C by R will be this. So that's all for today's class, for today's lecture. In our next lecture, we will discuss on time response analysis, step, ramp, impulse response of a first order system. Next, we will discuss on step response of a standard second order system for different damping conditions, that is under damped, over damped, like this. And next we will discuss on transient response specification of a standard second order system. So that's all for today. Thank you so much. Thank you for watching.